Hello everyone. So this is the first video in the series of lessons in particle physics. So by the end of the lessons, hopefully if you would go through all of them, I hope that you would appreciate particle physics more and uh, you would get to know what the universe is really made up of. So uh, you don't need a deep background in physics to understand concepts here. Maybe a little bit of quantum and nuclear physics would help, but overall, even if you have no background in physics, I think you can still follow the lessons here. So, the first one we're gonna learn about is Yukawa's Mesons. So way back in 1935, Hideki Yukawa, a Japanese physicist, he predicted the existence of a particle that mediates the strong nuclear force. So he said that uh, he predicted that there should be a particle that is, you can think of it as a messenger for this strong nuclear force. So for instance, in the electromagnetic force, um, it is mediated by particles known as photons. So here in this figure, we have a what we call a Feynman diagram. So this Feynman diagram is used in uh, particle physics to represent how particles can be treated uh, as interactions between other particles. So in this diagram, you can think of it as having an x-axis going to the right and a time axis going upward. So we know from electromagnetism that like charges will repel. So for instance, if you have two electrons that will be brought close together, as time progresses here upward, of course, they will experience a repulsion. And that repulsion is mediated by this particle, which we know as photons or light. So this photons or light is different from the one that we can measure experimentally. Uh, it's different by means of that we cannot detect it. So it only occurs for a very short period of time, such that there's no experimental evidence that there's no experiment that can detect it. Detect it. So we call those photons as virtual photons. So just like how photons mediate EM force, the electromagnetic force, there is a particle predicted by Yukawa which mediates the strong nuclear force. So for instance here you have a proton and a neutron which is binded inside the nucleus of an atom. So this particle, which he called the meson, which means medium mass, is the one responsible for the binding of protons and neutrons inside the nucleus. So, in order to predict the existence of mesons, he first tried to predict what is the mass of a meson. So Yukawa used the uh, uncertainty principle stated in terms of energy and time to estimate or approximate the mass of the meson. So here's the uncertainty principle. So if you have a proton, one proton here, for a meson to be present inside this system of proton and neutron, energy must be created. So likewise, mass must be created, and we know that energy and mass are equivalent from the equation E equals mc squared. So this will violate the law of conservation of energy, but for a limited amount of time. So this uncertainty principle will tell us that creation of an energy or a particle, in this case a meson, is possible, but only for a limited time of life. And the product of this uncertainty in energy and in time should be greater than or equal, always greater than or equal to this constant h bar over 2. So let's try to compute for the approximate mass of the meson. So we know that this energy can be expressed in terms of this formula, E equals mc squared. So multiplied by delta T. So what is delta T? So you can think of delta T as the time at which the meson can only exist in the nucleus, or to the time that which it is created, and at the same time it is disappearing inside the nucleus. So you can compute it as here or not. So you can think of this as distance over velocity. So R naught is the approximate size of nuclei of the nucleus. C, we put C here because we would assume that the mesons travel at near the speed of light, and we would divide by 2 so that the particle only travels half of the size of the nuclei. So by those two variables, we can compute how much time can the meson live. So we have now mc squared times r naught over 2c equals h bar over 2. And if we solve for mc squared, we would see that it is equal to 130 mega electron volts. Or in terms of mass, we can write it as MeV over c squared. So a side note in particle physics, most of the time, the masses of particles is expressed in terms of energy over c squared. So this is the approximate mass as computed by Yukawa. So this mass is of the meson. So to compare it with other particles, the mass of the meson is 250 times greater compared to that of the mass of the electron. So the mass of the electron is only 0.51 MeV per c squared.